Hello guys, my name is Lazaro and today we're going to be doing a LeetCode problem. This problem is called Number of Provinces. There are n cities, some of them connected while some are not. If city A is connected directly with city B and city B is connected directly with city C, then city A is connected indirectly with city C. So that's basically saying we can find a path from city A to city C. It might not be a direct edge from city A to city C, and we might have to travel multiple edges. So that path length might be of just one edge, or it might be multiple edges. A province is a group of directly or indirectly connected cities and all the cities outside of that group. So now they're just defining what a province is, that's part of the title. So this is pretty helpful. They're really just letting us know what they're asking for. You're given an n by n matrix is connected, where is connected I of j is 1 if the ith city and the jth city are directly connected, and is connected ij is 0 otherwise. So pretty much they're passing us a adjacency matrix, which is really helpful because they're basically representing the graph for us. Now they want us to return the total number of provinces. So if we remember, a province is a group of directly or directly connected cities. So if we look at the first example, 1 and 2 is connected, so that's one province. Then 3 is a whole province by itself, therefore the answer is 2. The second example, we have 1 is connected, it's connected to nothing, so it's all by itself. The same thing for 2 and 3, therefore the answer is 3. Now, what this problem is really asking us is the number of components in a graph. The number of components in a graph, let's say we have a graph that looks something like this. Doesn't have to be a tree. There could be some cycles. Let's say that's one graph. Then we have another graph over here. Then one there. There we go. So if this is our total graph, the number of components we have here is 1, 2, 3, and which color did I use? Oof, I don't like using the green, but that's what we have to. And 4. So we have 4 components here. And that's exactly what this problem is asking us to find, the number of components in this graph. Now this is actually a pretty common algorithm for graphs. Uh, so it's good that you guys are practicing by doing this problem or looking at this video. So how can we find the number of components? Well, the simple answer is a DFS on every single node that we have not seen. So let me explain what I mean by that. Let's have a table over here called seen nodes. Let me also label all of them. Perfect. So let's say we first start counting. We have a for loop. So for u in range of 1 all the way to 12. We will first start looking at 1. We have noticed that 1 is not a node we've previously seen. Therefore, let's run DFS on this node. If we were to run DFS and keeping track of all the nodes we've seen, we will see nodes 1, 2, 3, 4, and 5. So we finish our DFS on node 1. Then when we come back to our for loop, our next iteration will be number 2. We ask ourselves, have we seen node 2 already by looking at our set, for example? And since we've seen it before, we have already explored whatever component this node 2 is a part of. So we can continue and move to the next iteration. And this will be the case for node 3, 4, and 5 because we have already seen them previously. But once we get to 6, we realize that 6 is not a node we previously seen, therefore we run DFS on 6. We start on 6, then we go to 7, and then 8. And we add that to our seen nodes. Now since we finished our DFS, we can come back to our for loop. The next iteration will be 7. We've noticed that 7 is a node we've previously seen, so we continue. Next we move to 8. It's the same case, we've previously seen it. And now we move to 9. At 9, we've noticed that 9 is a node we have never seen before, therefore we run DFS, and we only get 9. Finally, when we're at 10, we notice 10 is not a node we've seen, so we run a DFS on 10. We will get 10, 11, and 12. At 11, it's part of our seen node, so we don't run DFS, we use continue. At 12, that's the same case, it's part of our seen nodes, so we don't run DFS, we continue. And we have successfully finished our for loop. Now notice the amount of times we've ran DFS is exactly equal to an amount of components we have in this graph. So how many times did we run DFS? Well, this is 1, this is 2, then this is 3, and finally this is 4. And if you remember, we have 1, 2, 3, and 4 components. So that's all it takes to solve this problem. If we have seen a node we have not seen before, let's run DFS on it and see all the nodes that are connected to this one. For all the nodes that are connected to this one, we can consider this one province or one component. And then let's continue going through all the other nodes. And let's see if there's one node that we have not already seen. We know that that node was disconnected from the rest. Therefore, we have to rerun DFS, and we have just seen a new component. So like I said, this is a pretty common graph problem, the number of components, and it's extremely useful to know this or to have this in your tool belt. So now that we talked about it and we explained it, let's actually write the code. First, let's define n, where n is the length of is connected. First, let's remember the is connected is an adjacency matrix, so we can really just use this is connected list as our graph data structure. We don't have to create another data structure that represents the graph. First, let's get the amount of nodes there is, which is equal to the length of the is connected matrix. Then let's also create that set, that scene set that we mentioned. And let's create our DFS function. So if the current node we're on is in our set, then let's just return. Else, let's add it to our set. Now, for every node in the graph, if is connected for this current node and to this adjacent node, we can call this B actually. If this is equal to 1, then we know there's an edge from U to B. Therefore, let's call DFS on B. That's really all that is needed for a DFS function. Other than that, let's just create a variable called answer, which is going to represent the number of components there are. Now for u in range of self.n, for every node in this graph, if we have not seen u in our set, then let's run DFS on it. And let's also increment our answer variable. Finally, let's just return answer. This is all that is needed, so let's run the code, see if I made any mistakes. No? Alright, let's try other test cases. Perfect, and now let's submit. Awesome, and it's accepted. So like I said, this problem is actually really common and really important to know. So make sure you guys fully understand this solution and this algorithm. Other than that, I hope I was able to help you guys understand it or help you in any way possible. So thank you guys for watching. If you enjoyed it, then please leave a like and consider subscribing. Thank you very much.